In this video, we are going to explain what are pushdown automata and how are they related to context-free languages. The last type of automaton we've seen is called finite automata. We showed that for regular languages, it's powerful, but unfortunately it has a limited memory, so that we cannot use it to recognize context-free languages. For example, if we want to recognize the strings a to the n, b to the m, we already have seen that this string a to the n, b to the m may be recognized easily by the nondeterministic finite automaton with two states. In the first one, we have a self loop with the symbol a, and then in the second, we have a self loop with the symbol b. Now, if we want to recognize the same type of strings, but with the same number of a's and b's, a to the n, b to the n, with the same n here in exponent, is impossible to recognize via this automaton because this NFA cannot count. So the idea here is to use a stack with an automaton. We will use the same machine here, and we will add a stack in which we may save some information to use in the future. For example, here to recognize AAA followed by triple B, we may use a stack to save, for example, the 3 A's in the first part of the string, and we will use this information in the stack to recognize the second part of the string. So here we have introduced to the concept of pushdown automaton. So this automaton consists of having the same possibility that we have already seen with finite automata, which is a set of states with some transitions between them. And then this machine will read the input from a tape here. We will put all the symbols of the input in a tape, and we will have the possibility to use a stack. You can think of stack as a device in which we can put elements of the same type on top of each other. Think about, for example, a set of dishes in a restaurant where we will put them on top of each other. And when we have a new dish, for example, to put, we will put it on top of all the others. And if we want to take off one plate, for example, we will have to take the one on the top, this one. If we want to access to this element, we need to take off the first one here that appears on the top, then remove this one, and now we will have access to the needed element. So here is simply the idea of stack. We have two possible operations which are pop. That means we will read and remove a symbol from the stack. And this symbol is on the top. The second operation is push, and this means that we will write a symbol on top of the stack. So we will use these two operations in a pushdown automaton. For example, for the idea of recognizing the set of strings a to the n, b to the n, we may say that we will read the a's from the input and push them in the stack until we read the b. Then we will read the b's and pop one a with each b. So in this case, we will guarantee that the number of b's read corresponds to the number of the symbol a. For this example of input AAA, triple B, we will read the first symbol here, and since it's the symbol A, we will push it. So we will push the first symbol A on top of the stack. Then we will see again the symbol A. So according to this rule, we will push it. Then we will find another A, and also we will push it. Okay, now since we'll see B in the input, so this B will correspond correspond with this A on top of the stack. So the operation here will be pop. With the second symbol also we will pop the symbol A on top of the stack, and with the third B also we will pop the symbol A in the stack. And finally we will accept if we have completed already the input, all symbols of the input are red, and the stack is empty. After clarifying the idea behind the pushdown automaton, let's formally define what is it a pushdown automaton. So this type of automaton consists of a 6-tuple Q, sigma, gamma, delta, Q0 and F, where Q is a set of states, sigma is a set of input alphabet, just like for finite automata here. Also, Q0 and F are respectively the initial state and the set of final states, just like for finite automata. Now we've added here a set of symbols of the stack. Since we will have a stack, we will push or pop symbols on it. We may use the same symbols as sigma, but also we may use other symbols. Then we will have also a new definition for delta, the transition function here. So delta will take as input 3 information: the state, the symbol to read from the input, and the symbol to read on top of the stack. So this symbol on top of the stack will be read and popped. It will be removed from the stack. The output will be Q cross gamma, because we'll give what is the next state and what is the symbol to be written in the stack, the symbol to be pushed. And this information may be written in the automaton as follows. So we will have a transition from state Q to state P, and with this transition we will need to read a symbol of the input X. We will also need to read a symbol from the stack, which is the symbol on top of the stack. So these are the 3 information from the input of this transition function: the state, the symbol from the input, and the symbol on top of the stack. And the output will be here the next state. Here it's P, and the symbol to be pushed, the symbol to be written on the stack. Okay, as you may see here, we may have different possibilities for this result of transition. That's why we used in the definition the power set of Q cross gamma epsilon. And this is known as the possibility for non-determinism according to this definition. Okay, also we have used here sigma epsilon and gamma epsilon here. Why we used epsilon here? Because we will allow for a transition without consuming any symbol of the alphabet. So if we write here epsilon, it means we will take this transition without reading from the input. Also, this epsilon is used here for the symbols to be popped or pushed to the stack, because we may have a transition that will not influence on the symbols of the stack. If we use here epsilon, it means we will not pop any symbol from the stack. If we use here epsilon, it means that we will not push any symbol to the stack. That's why we used in the definition here sigma epsilon and gamma epsilon in the case of the symbol to pop, or also the case of the symbol to push. Now let's use this information or this definition to draw pushdown automaton for the language A to the N, B to the N. So if we want to recognize the set of strings in the form A to the N, B to the N, we will use the stack as we've seen before. We will split the string into 2 parts. For example, here if we have 4 A's followed by 4 B's, the idea is to split this into 2 parts. the first part with A's. With each A, we will push a symbol A on the stack. And for the second part here, with each B that will be red, we will pop a symbol A from the stack. Now, since in the beginning and at the end of this work, the stack is empty, we will start from this symbol with an empty stack, and at the end, we'll check if the stack is empty. So we need some way to say that the stack is empty or not. In the formal definition given above, we don't have anything related to a test if the stack is empty. So we need just here to find a way to recognize if a stack is empty. So for example, we may here push at the very initial step here, a dollar sign, for example, any sign that if we find it again on the stack, this means that there is no symbol in the stack. Okay, let's say, for example, from the initial state here to the second state, we will just push the symbol dollar on the stack. Okay, we will not pop, of course, the stack is empty, and we will not read any symbol of the input. Now, in the state B, we will read these A's. We will allow here for a loop to read all the A's. And with each A read here, we will not pop any symbol of the stack, but we will push the symbol A. Then we will go to a state C, in which we will read the second part of the string, and with each B read here, we will pop a symbol A of the stack. Okay, we will push nothing, so we have written here epsilon. Once we've determined this part of the letters B, we will check if on top of the stack we have the symbol dollar sign. If we have dollar sign here, we'll go to an accept state D. Of course, here it's an accept state, but we will accept only if we have already completed all the symbols of the input. So here, being in a final state will matter only if all the symbols of the input have been already read. Let's note here that this language accepts the empty string, since n here may be equal to 0. In fact, we can easily check that epsilon is already accepted by this pushdown automaton. You remember when we say that we will split the string into two parts, and we assure the recognition of the first part via this self loop and the recognition of the second part via this loop. In between, from B to C, we have this transition, which states that we will go from B to C without reading any symbol, and also we will not change anything on the stack. So we will accept the empty string, since we will go from A to B with just pushing the dollar sign, and then we will go from B to C without doing anything, and then from C to D we will have already the dollar sign on top of the stack. So this transition also will fire, and epsilon will be accepted. Now, if we want to accept the epsilon string, if the language will accept A's followed by B's, and at least there will be one A and one B. So the list string here will be A, B. In this case, we can also use this transition. This will guarantee that we cannot go from B to C unless we see a B in the input. And also, there is a A on top of the stack. And this A means that we already pushed a symbol A on the stack. And remember, we are pushing a symbol A only if we read the symbol A in the input. So this transition from B to C is possible only if we already fired this self loop at least once. And this is how we claimed that there will be at least one A and one B in the input. Of course, if there's more than one A and one B in the string, to recognize the good number of the two symbols. For all the A's red, there will be exactly the same number of A's that will be pushed on the stack. And for the B's, the first one, it will pop a symbol A via this transition, and the rest of the B's will pop other A's by firing this self loop. And we will not be able to go to the final state only if we will encounter $sign on top of the stack. Now to check if a string is recognized by a pushdown automaton, there is a rigorous way which consists of tracing what will be the state, the input, and the stack after each transition. So initially we'll be at the state A. The input will be, for example, here triple A, triple B, and the stack is empty. For the first transition here from A to B, the state will be B. The input is the same, will not consume any symbol of the input, but the stack will contain the symbol dollar since it's pushed via this transition. Then from B, since we will read the symbol A here in the input, so according to this transition, we will push A. So in the stack, we will find the symbols $A. Here, for sake of simplicity, we'll write $A from left to right, which means that the symbols are pushed in this way. The first time we pushed dollar, then we pushed A, and the symbol to the right here will be the next symbol to read from the stack. For the input, we advanced one symbol and we removed here the A that has already been read. So now for the next transition also, since we are seeing the A here, we will remove this A from the input and we will push a symbol A to the stack. The state is always B. Again, we are seeing the symbol A here. So the next state will be B, and the next symbol to read will be this small b, and we have another symbol A that is pushed to the stack. Now, since we have a B here, we cannot fire again this transition, so we'll move from B to C. We will record here the next state C. The input will not be changed. We will not read any symbol of the input, and also the stack will be the same. We will not pop and neither push any symbol to the stack. From C, since we are seeing B, the next state will be C. We will advance the input to the next symbol, and we will pop the symbol A, which is on the top of the stack. Then again, we will apply this transition, which means that we will go to the next symbol of the input. The next state will be C, and we will pop a symbol A from the stack. Again, we will apply the same transition since we will see this B, and since all the input is finished, so we will write here epsilon, and the next state will be C. For the stack, we will pop the symbol A, so we'll find only dollar. And now we will be able to apply this transition, which means that we will pop the $sign, so we can say that this input will be accepted. Now, if we take this input, AAA double B, we will do the same. We will find here that when the input is finished, we will find that we still have another A on top of the stack. So we are blocked here in the state C. We cannot advance to an accept state, even if the input is completed. So AAA double B will not be accepted. Let's take a final example here to insist on the fact that an input is accepted only if a final state is reached and we are at the end of the input. So for this example, AA, if we trace the content of the state, the input and the stack, we'll find at the last stage here that we have reached the accept state D. In the input, we still have a symbol that is not read and the stack is empty. In this case, we will not accept this input. After defining what are pushdown automata and showing how are they used to recognize context-free languages, let's now state a very important theorem, which is a language is context-free if and only if it's recognized by a pushdown automaton. If and only if means two directions to prove. We have the first one, which states that if L is context-free, then there should be a pushdown automaton, which is a recognizer for this language. And in the second direction, we have if the language is recognized by a pushdown automaton, then this language should be context-free. And by definition, recall that a context-free language is a language that is generated by context-free grammar. So for a proof to this theorem, it is sufficient to show that we can convert from a context-free grammar to a pushdown automaton and vice versa. In the next video, we will explain how and why context-free grammars can be easily converted to pushdown automata.